If this type or group of vectors represent a subvector space? Yes or no? It doesn't have an origin. The origin is going to be different. Okay? So, if I want to study this case, you will remark that each two vectors on this case, they will satisfy the additivity. Okay? And maybe they will bring, I think, it will break the multiplication by scalar, and also it will break the zero existence. Because the zero of this form of vectors is going to be a 0 and 1. Okay? Not with the origin of R2, which is 0, 0. And so it's not a subvector space. This part, all the previous part that I talked to you about, or we went together through it, it's not in the slides of Lisbon. From here, starting the slides of Lisbon, I had to go through them to make you understand, or to gather the simplest way to gather the main idea of a vector space, which is really very simple. It's a bunch of some things. Those things should satisfy addition and should satisfy multiplication by scalar to have the same shape, plus the existence of the origin. How to be a subvector space? The first two operations already exist, plus a conditions, they share the same origin with the main vector space. Okay? Let's see how they are. First of all, let E be a non-empty set, and the K, we already know from the first lecture that K represents numbers maybe real or complex. Okay. Assume that we have defined two operations. One that we denote by sum. The operations of sum, which means plus, such that I will have cross of two vectors is equal to 2, which means A and B will lead to A plus B. It's the binary operation in addition. Plus the multiplication by a scalar. This is the addition, and that's the multiplication of outer multiplication. Okay, we said that E ended with these two operations is a vector space over K. It's a vector space over the K value. Why we say over K? Because K may be real numbers or complex numbers. Okay? Maybe. That is E is a vector subspace. Under how many operations? Two operations. The addition and the multiplication. Of course, the outer multiplication. It's a vector space over K. Okay, the sum verifies the following probabilities, which are the probabilities associated with the addition of two vectors. The first of them, UV belongs to E, so you have the addition, you have the commutativity, the distributivity, the existence of an origin, and the existence of an inverse of a vector. U plus negative U is going to equal to a 0 of E. The outer multiplication also, it means multiplying a constant in U or in V, it will result in a vector belongs to this set of vectors, or the distributivity of a constant through the addition, or adding alpha plus B times U distribution on various constants. All of this we already did go through it. These are the main conditions for the sum verification and the multiplication by a scalar, exactly as we saw previously. Okay, we denominate the elements of E by vectors. We denominate the elements of K by scalars. If K equal to C, say that E is a complex vector space. If K equal to R, we say real vector space. So I will have the complex vector space, the real vector space, based on the value of the scalars that we are dealing with. Okay, R is a vector space over R, C is a vector space over C complex, C is a vector space over R. Okay, this also some information which is really very important, because we look to the real number as a subset from the complex numbers. Okay, you have the real numbers and you have the complex numbers. The real numbers are already contained in the complex numbers. Do you remember the complex numbers? Each one of them, it contains a real part plus the imaginary part. So already the real numbers are a part or a subspace from the complex space. Okay, but R is not a vector space over C. So this statement is really very important. C is a vector space over R, but R is not a vector space over C. It means R is a subset from C, but C is not a subset from R. Okay? All the matrices M and N with usual sum between matrices and with the usual multiplication of an element of K defined in chapter 1 is a vector space over K. And we already explained this in points. K to the power of N with usual sum of N tuples defined by the following tuples means components. Also, it is a vector space. The set of polynomials, this is very, very important. The set of polynomials can define, define a vector space. So the expression of vector spaces is not just only related about the vectors, it's objects also. So let's think of the quadratic polynomial. زياد انت عارف يعني ايه quadratic polynomial؟ اللي هي ايه؟ اللي هي 2x square plus 3x plus 4 صح؟ x square plus 5 مش كده برضو؟ By the idea x plus 2 is a quadratic. Why? X plus 2 is a quadratic. From this concept, it contains 0x square plus bx plus c. So the set of polynomials kn of x, if I'm targeting the grade or the degree of these polynomials, it will represent a vector space. Okay? When a1 up to an belongs to either real or complex numbers. شباب انتوا معايا؟ اي مجموعه polynomials هيتحقق فيهم قد ايه؟ الكونديشنز. A polynomial of second degree is not going to be added unless on a polynomial of second degree. And the result will be polynomial of second degree. A polynomial of second degree, if you multiply by a number, the result will be a polynomial of second degree. A polynomial of second degree, it contains a zero. Where a1 equal a2 equal a3 equal 0. So it's already a vector space. Okay? Kn with usual sum of polynomials, he's proving this for you as I did exactly, and with a multiplication of an alpha also will result. So is a vector space over K, the set of them. Okay, we denote Kx as the set of polynomials in one variables without coefficient K, no restriction on the degree once more. The set of all points on the plane or space, if we have a set of all points on the plane or space, but under the condition that passes through the origin, it also will be a vector space, and that's the addition of two vectors. Let A be a vector space over K and alpha and U. The following statements hold. The neutral element of the sum in E is unique. This is exactly what we said. The neutral, which means the identity, like the 0, 0, 0. For each U belongs to E, the opposite of U for the sum of E is unique. And that's exactly what we did. If we have 1, 1, 1, you will have also negative 1, negative 1, negative 1. That's unique. You can't find more than vector on this sheet. The existence of the origin of a vector subspace, and if you multiply in a negative, the result will be also belongs to this vector space. I will stop at here. Let's stop at this slide, and I will continue tomorrow. Bottom line for what we did go through. We already now know the condition for a vector space, the conditions for subvector space. They are the same between the two slides. I believe I sent you the Lisbon slides yesterday. I'm not really sure, but I will check once I check my WhatsApp. I already sent you this. I will finish those ones, or the work of this week, and I will send it to you by the end of this week. Then the second part will be within the next week, inshallah. Thank you very much. And please do go through them step by step. Once you try to memorize these conditions, it's going to be easy, okay? For the next tomorrow's lecture, inshallah. Thank you.